Hello guys, so we're here to evaluate triple integrals in other coordinates. Specifically, the one I'm doing right now is cylindrical coordinates, where dz is 0 to e to the negative r squared, r is 0 to 3, and theta is 0 to pi over 2. Now, to better understand this, let's look at it in the rectangular coordinates first. Let's draw the xyz plane. Y, z, and x. Okay, so let's start with the theta, which is from here, the limits of the integration said it's 0 to pi over 2. Okay, that basically means it's half a circle. Okay, let's do that right here. A quarter circle, I meant, sorry about that. And okay, that's the quarter circle. And on the other hand, let's look at dr, which is 0 to 3, and which r is basically the distance from the origin to the circle. Right here, 0 to 3, 0 to 3. Okay. And then lastly, we can look at the z, which is e to the negative r squared. If you think about that, this is what it'll look like, in which natural log looks like this, and then the negative r squared make it look like that. To make us understand this even better, we can draw the xy curve plane, which is yx. Okay, so this is the xy plane, and here we can look at it like this: 0 to 3, 0 to 3. If you do it normally in rectangular coordinates, we have x from 0 to 3, while y as a function of x is radical 9 minus x squared from 0, right? And lastly, we have z here. Z. For the z, we have as r squared. In terms of rectangular coordinates, we can look at it as e to the negative x squared plus y squared. That's where it came from, where x squared plus y squared is equal to r squared, which is this 0 to 3, and the y as a function of x is this 9 minus x squared, and then x is 0 to 3. Okay, now that we understand that, let's go integrate. So 0 to pi over 2, 0 to 3, and then okay, here's the function r dz dr d theta. So we evaluate z first. That means r is a constant, so we just do it normally, like r z evaluated from 0 to e to the negative r squared dr d theta. Okay, so we plug e to the z, 0 to the z. Okay, 0 to pi over 2, 0 to 3, and then r is a constant, so e to the negative r squared minus 0 dr d theta. Okay, 0 goes away, so 0 to pi over 2, 0 to 3, so r e negative r squared dr d theta. Okay, now we evaluate in terms of r. With here, At first glance, it looks like integration by parts, but if we think about it, we can actually get away with a u sub. Okay, let's do u sub. With u being negative r squared, now take the derivative, du is equal to negative 2r dr, coming from here. Okay, now we have r here, dr here, and we can take out the negative 2 to the other side. Negative 1/2 du r dr. Okay, now let's substitute. Not forgetting about the limits of integration. If r is 3, u is 3 squared is 9. We have a negative, so negative 9. And if r is 0, we have 0 squared is 0. Okay, then we have a constant here, negative 1/2 r dr here goes away, and then e to the u, du d theta. Okay, now let's evaluate. 0 to pi over 2, negative 1/2 e to the u evaluated from 0 to negative 9 d theta. Okay, let's plug negative 9 here, 0 in here. Okay, 0 to pi over 2, so negative 1/2 e to the negative 9 minus e to the 0 d theta. Okay, so negative e to the negative 9, that's a decimal. E to the 0, that's 1. So we have here 0 to pi over 2, constant negative 1/2, and then we have e to the negative 9 minus 1, e to the 0, 1 d theta. Okay, last but not the least, we can take out this negative 1/2 to the left, so negative 1/2 0 to pi over 2, and then here's the function e to the negative 9 minus 1 d theta. Okay, so we can integrate again in terms of theta now. So negative 1/2 e to the negative 9 theta minus theta evaluated from 0 to pi over 2. Okay, and then we plug pi over 2 here, pi over 2 here. So we have the constant here, negative 1/2. Put a bracket here. E to the negative 9 times pi over 2 minus pi over 2 minus, we have here e to the negative 9, 0, and another 0. Okay, and then this one goes away, so we have negative 1/2 e to the negative 9 times pi over 2 minus pi over 2. Okay, now let's just simplify. We can take pi over 2 out, negative 1/2 times pi over 2 minus e to the negative 9 minus 1. Simplify again, negative pi over 4 e to the negative 9 minus 1. Here's the final answer, and we can even calculate that. Should we? Let's do that. Take the calculator out. So we have negative pi over 4 times e to the negative 9 minus 1. So it's 0.79. Here's the final answer. And that's triple integrals in cylindrical coordinates. Thank you.
Let's try an example. Evaluate the triple integral from negative 3 to 3, negative 9 minus x squared to 9 minus x squared, and from the square root of x squared plus y squared to 3, dz, dy, dx. To solve this problem, it's going to be very helpful for us to get our bounds for x, y, and z. And so let's get it first in rectangular coordinates. As we see here, dx corresponds to the bounds over here, so the x bounds will be negative 3 to 3. dy will correspond to the bounds over here, which means that it'll go from negative 9 minus x squared and the square root of 9 minus x squared. The other one's the square root as well. And z will go to 3 from the square root of x squared plus y squared. Now, we're going to want to convert this into cylindrical coordinates. And so what might be very helpful to us would be to draw the x and y plane, the xy plane on the side. We see that in the x direction it will go from negative 3 to 3. And in the y direction it will also go from negative 3 to 3, or that will be the max bounds. And it will make something like this, a circle up there. If we look in the x, y, and z plane, it will look something like this. That looks like it will go up to until 3 as a cone, and will go something like this, something like that, and where this circle is the one right there. Now we are going to want to find these bounds in cylindrical coordinates so that we can rewrite what we're given here in cylindrical coordinates instead. As we look at this circle over here, we see that it goes from 0 to 2 pi in theta. And so we can say that the bounds for theta will be from 0 to 2 pi, a full circle. As we look for the bounds of r, we can see that from the origin it always goes out 3 units, which means that the bounds for r will be 0 to 3. Now for the bounds of z, we can recall that for cylindrical coordinates, x squared plus y squared equals r squared. Therefore, if you look at the coordinates over here, the z will become the square root of r squared to 3. And that's just going to be, which I'll write over here, r to 3. Now, rewriting the problem, we can write it as from 0 to 2 pi, 0 to 3, and r to 3, dz, dr, d theta, corresponding to the bounds over here, and you want to end with one of the constants. And now, since we switched it to cylindrical coordinates, we have to include a Jacobian, which would be an extra factor of r. Now that we have this equation, we're just going to have to solve it, and I'm gonna write this up here instead, which will be 0 to 2 pi, 0 to 3, r to 3, r dz, dr, d theta. And the first thing we're going to want to do is this first integral, so from 0 to 2 pi, and then from 0 to 3, this integral is with respect to z, and so it will be rz evaluated at r3, dr, d theta. This one should give us the integral from 0 to 2 pi, the integral of 0 to 3 of 3r minus r squared, dr, d theta. Now we're going to want to do the second integral, which will go from 0 to 2 pi of 3 over 2 r squared minus 1/3 r cubed evaluated at from 0 to 3 d theta. That should give us, if we do that, it will be something along the lines of 27 over 2, from 0 to 2 pi. 27 over 2 minus 27 over 3 d theta, which gives us from 0 to 2 pi 9 over 2 d theta. And then, so when the theta comes in, it'll be 9 theta over 2 evaluated from 0 to 2 pi, which should give us a final answer of 9 pi. And there you have it. Let's try another example. Evaluate the triple integral from 0 to 3, 0 to the square root of 9 plus x squared, and 0 to the square root of 9 minus x squared minus y squared of the square root of x squared plus y squared plus z squared dz, dy, dx. Now we're going to start it off by writing the bounds in the rectangular coordinates given to us, where we see dx corresponds to 0 to 3. dy corresponds to this one, which is 0 to the square root of 9 plus x squared. And z corresponds to 0 to the square root of 9 minus x squared minus y squared. Again, drawing on the xy plane, so it'll help us with our bounds later. X will be from 0 to 3 in this direction. And y will be from 0 to 9 plus x squared, but because that's going to be over here, because x is only from 0 to 3, and it'll go down like that. Okay, now we're going to want to get our bounds in spherical coordinates, which will be rho, phi, and theta. Now, because we can see here that from the origin it goes out 3 units, we'll know that the bounds for rho will be from 0 to 3. And since we see that it only goes 1/4 of a circle rather than the regular full circle, it will go from 0 to pi over 2. The bounds for phi will be 0 to pi over 2 as well, because we only go from 90 degrees of the circle rather than 180 or 360. Now, we're going to want to switch this part of the equation into cylindrical coordinates, or spherical coordinates as well, I apologize. And to do this, we'll want to remember the fact that x squared plus y squared plus z squared equals r squared. Rho squared, I apologize. There you go. Now, when we look at that, that means that we can change the inside integral to become the square root of rho squared, which will just equal rho. And since these are all constants, it's really nice, so we can move them around as well. That means that we can rewrite it as from 0 to pi over 2, 0 to pi over 2, and 0 to 3 of rho, and then d rho d phi d theta. But because we converted into spherical coordinates, we're going to have to add an extra factor of rho squared sine phi. And so we will work with this to integrate. Okay, and now I rewrote it over here. I did make a little I misspoke a little bit over here, where it should have been to phi, but it's now been rewritten as phi over there, and so let's move it over on that side so that it can be integrated. Now this inside part of the equation can be, the first integral we're going to want to do, can be simplified to rho cubed sine phi. And we're first going to do it with respect to rho. And this parts don't go away. I'm just writing them afterwards because you just copy them down. Now, to do this one, we're going to end up with rho to the 4th over 4 sine phi evaluated at 0 to 3 d phi d theta, with these bounds still here waiting for their time to shine. And this one should come out to be from 0 to pi over 2, 0 to pi over 2, 81 over 4 sine phi, as sine phi. Again, this is supposed to be a sine phi, I apologize. D phi, d theta. And now we can integrate with respect to phi, which will make it 0 to pi over 2, and negative 81 over 4 cosine of phi, from the evaluated at 0 to pi over 2 d theta. Now, because we're going to go cosine of 0 will be 1 and cosine of pi over 2 will be 0, we actually end up with 0 to pi over 2 of 0 minus negative 81 over 4 cosine of phi, or well, that cosine of phi can be simplified to 1, so just negative 81 over 4 d theta. That can be simplified to from 0 to pi over 2 of 81 over 4 d theta, which ultimately should come out to be 81 pi over 2 times 4 minus 0, which should equal 81 pi over 8. And that's your final answer.